Welcome to A-Level and AP Physics. In today's lesson, we will discuss past paper questions from October-November 2022, paper 4, variant 2. In this lesson, we will discuss question number 6 and question number 7. Question number 6 is from capacitance and question number 7 is about electromagnetism. In our today's class, we will discuss these two questions in detail so you can improve your conceptual understanding of these two topics and also you can have better understanding of these two questions. If you really want to get higher grades in your exam, you need practice. And for practice, I have uploaded about 40 past papers, paper 4 past papers with full solution on my channel. If you go to A2 playlist, you can find about 40 past papers with full solution and detailed solution. I have explained every point in detail. If you watch those 40 past papers, you will improve your conceptual understanding, and I'm quite confident most of you will be able to get A star or at least A. If you listen those videos carefully, take notes and try to improve your conceptual understanding. And also, when you watch those videos, if you have any questions, you can leave your questions in the comments and I will be answering as soon as possible. I hope you will watch those videos and you will improve yourself. For the remaining questions from this paper and also from paper 4.1 from October-November 2022, I will be uploading solutions as soon as possible. Let's study together. Let's improve together. For question number 6, it is given to us a capacitor of capacitance capital C and a resistor of resistance capital R are connected as shown in figure 6.1. Initially, the capacitor is charged and the switch is open. The switch is then closed at time t is equal to 0. Figure 6.2 and figure 6.3 show respectively the variation with t of the charge on the capacitor and the potential difference V across the resistor. So we have in this case the charge against time graph and we have potential difference against time graph. For part A, we need to explain the shape of the line in figure 6.3 representing the variation of V with T. For this question, it is given to us that the capacitor is initially charged. So we can simply draw these positive charges on one plate and we can draw equal amount of negative charges on the other plate. So this is telling us the capacitor is charged when the switch is open. And also we can see the value of potential difference across capacitor. This is value of potential difference across resistor, but potential difference across resistor delta VR at any instant, this one will be equal to the potential difference across capacitor at any instant. So this is one very important point you need to understand because they are connected in parallel. So the potential difference across capacitor will be equal to potential difference across resistor at any given instant. So when potential difference across capacitor will decrease, means after closing the switch, potential difference across resistor also will decrease. At time t is equal to 0, when we just close the switch, at t equal to 0, when we just close the switch, potential difference across resistor is equal to potential difference across capacitor, and value of that potential difference we can find from here, and this value is 7.5 volts. So simply we can say initially potential difference across capacitor is equal to 7.5 volts and potential difference across resistor initially is also equal to 7.5 volts. Now we need to understand what is happening to potential difference with time. So if we look at the potential difference across resistor, this is decreasing with time. So it means the potential difference across capacitor is also decreasing with time, and shape of the graph will be the same. Potential difference will be decreasing. So we can close this switch. So we close this switch. Now if we also look at this potential difference across resistor, potential difference across resistor, this is delta V times R and this will be equal to I times R, means current passing through this resistor. As the potential difference across this one is decreasing with time, it simply means that value of I is also decreasing with time because resistance of capacitor is constant. So these are some basic points we are trying to understand. Next one, how about potential difference across capacitor? Potential difference across capacitor, delta V, this one will be equal to the charge on the capacitor divided by capacitance of capacitor. Means simply Q is equal to CV. As capacitance of capacitor is not changing when this capacitor will discharge, this is constant. It means the charge on capacitor plate means the net charge on any plate that is also decreasing with time. So these are some basic points we need to understand. Now let me show you one simple animation to explain this process in detail. You can simply look at this animation. In this case, you can see the positive charges. They are moving from the positive plate. Actually, you can understand negative charge. Actually, negative charge flow, positive charge does not flow. But we take assumption of conventional current. That's the reason in this animation you can see positive charges, they are coming from this positive plate. So the net positive charge on this plate is decreasing and net negative charge on this plate is also decreasing because positive and negative, they negate each other. So the net charge is decreasing. We can also simply understand in this case, electrons actually move, not positive charges. So this is based on conventional current. So electron will go this side, so they will negate positive charges. So finally, charge on this plate and this plate, the net charge will be zero. So at that moment, delta VC, this one will be equal to zero and delta VR also will be equal to 0 because at that moment no current will flow. So we can say at t is equal to infinity, after a long time, I will be 0, current through this resistor will be 0, so potential difference across resistor will be 0 and delta VC also will be 0 because Q net charge on each plate of the capacitor also will be equal to 0. So capacitor will be fully discharged. So these are the points we need to understand. Now let's try to write down our answer. This question has 3 marks. So one point you can simply say that initially potential difference, we can say potential difference across resistor, this is equal to potential difference across capacitor. If you write on this one, you will get 1 mark. If you get potential difference across resistor, we have already discussed that potential difference across resistor is equal to I times R. As the potential difference across the resistor is decreasing, it also means that current is decreasing. Or simply we can say in this case, current is proportional to potential difference across resistor. So we can write down in this case current passing through the resistor, this is directly proportional to potential difference across resistor. As potential difference across resistor is decreasing with time, it means current passing through resistor is also decreasing. And we can also consider the potential difference across capacitor and potential difference across capacitor also decreasing because the charge on the capacitor, this is proportional to potential difference across capacitor. So in this case, PD across capacitor is decreasing. It means charge on the capacitor is also decreasing. So the potential difference across capacitor is decreasing. So it also means that the charge on the capacitor is decreasing. So finally, we can say that in this case, the rate of change of PD, the rate of change of PD across capacitor, rate of change of PD across capacitor is decreasing. Change of PD across capacitor is decreasing because PD across capacitor is decreasing. So we can say rate of change of PD across capacitor decreases as PD is decreasing. So if you write down these points, you will get 3 marks for this question. So you have to be very clear about concept. In this case, we have discussed some very important point. And the last point I want to explain you is that when the switch is open, at that moment, what is potential difference across resistor when switch is open? I hope you will say potential difference across resistor will be equal to 0 because when the switch is open, I passing through resistor is 0. It means at that moment delta V across resistor is equal to 0. But when we close the switch, PD across resistor and PD across capacitor is the same as we have discussed here. So if you have this much understanding of this discharging of capacitor, you can answer this question easily. I hope this one is clear to you. If you have any questions, you can leave your questions in comments. Let's try to summarize these points. How we have written our answer in this form. First thing we need to understand is that in the question it is given to you, PD across resistor is decreasing with time. And we need to understand, as capacitor and resistor, they are connected in parallel. It means PD across capacitor is equal to PD across resistor. So that's the reason we have written our first point. And the second point, now we need to talk about PD across the resistor, how PD across resistor is decreasing. PD across resistor is decreasing because current passing through the resistor is decreasing. So we have written the second point. And the third point, we can talk about how PD across capacitor is changing. PD across capacitor is decreasing. Why? Because charge on the capacitor is decreasing. So we have written our third point. And the fourth one, we need to talk about the gradient of this one, means the rate of change of PD. So in this case, rate of change of PD is decreasing because PD across resistor is decreasing. Now you can say PD across capacitor is decreasing. So this is the approach, how you need to approach this type of problems. I hope discharging of capacitor is clear to you. Now how to talk about discharging of capacitor. For part B, we need to use figure 6.2 and we need to show that time constant of the circuit in figure 6.1 is equal to 5.5 seconds. It simply means that we need to calculate time constant. So how we can calculate time constant if Q against T graph is given to us? So we need to understand this is a decay graph. So Q in this case, as a function of time, Q will be equal to Q naught e to the power of minus T over RC. RC is time constant. And in this case, time constant means tau. Time constant, this is equal to RC. So simply we can rewrite this equation. We can say Q as a function of time, in this case, is equal to Q naught e to the power of minus RC divided by RC. Or simply we can say this is equal to Q naught e to the power of minus 1. Now from here we can find out Q after 1 tau, means after one time constant. So we can find out value of Q after one time constant. So simply we have in this case Q naught, this is divided by E. What is initial value of Q naught? We can simply find from here. When time t0, Q naught is equal to 0.90 millicoulombs. So we can write on here, this is 0.90 millicoulombs divided by E. E is a constant. If we solve this, we will get our final answer is 0.33 millicoulombs. So now we have value of charge after one time constant. So simply we can find out charge from here and then we can find value of T. So if we look at this point, this will be equal to 0.25, this will be 0.30, this will be 0.35. So it is somewhere here. So at this point we have 0.33. So simply we can label here, this is value of the charge. So we need to find time constant. And so simply we can draw the line. In this case, we can simply draw the line from here. So it will intersect at this point. And then we can draw the line on time axis. Line on time axis. So in this case, value of time is about 5.5. So this is how we need to answer this problem. So simply we can say at Q is equal to 0.33 millicoulombs, time is equal to 5.5 seconds. So this is our final answer and this is how you need to show. So simply you can label on this one. You no need to write this part and you will get full marks. Means you will get 3 marks. For part C, we need to use figure 6.2 and figure 6.3 and the information in B to determine value of capacitance in microfarads. So we need to calculate value of capacitance. So what is capacitance? Capacitance is simply the ratio between charge on one plate, the net charge on single plate of a capacitor, divided by potential difference across two plates of capacitor. So this is the net charge on single plate of capacitor, and this is the potential difference between two plates. So in this case, if at any point we have value of Q and also we have value of V, we can find out value of C. For simplicity, we can take the initial amount of charge, initial net charge on the plates, and we can take initial value of potential difference between the plates. So simply I will say, in this case, I will take initial value of Q and I will take initial value of potential difference across two plates of capacitor. So from here, we can read value of Q, that is equal to 0.90 millicoulombs. So we can simply write down this is 0.90 millicoulombs. And we can read value of V from here. This is about 7.5 volts. So we can divide this one by 7.5 volts. Now this is millicoulomb. So we have to multiply with 10 to minus 0. And if we solve this one, our final answer in this case will be 1.2 times 10 to minus 4 coulombs, but we need to write down our answer in form of microfarad. So this will be not coulomb, this one will be farad because we are talking about capacitance. So this one will be in farad. Our answer has to be in microfarads. So simply we can multiply this with 10 to 2 and also we need to multiply with 10 to minus 2. So here we have this is 10 to minus 4. Now if we simplify this one, so 1.2 multiplied by 100, this will be equal to 120, and 10 to minus 2 means multiply by 10 to minus 4. So this is simply equal to 10 to minus 6 because these powers have to be added. Because these are multiplied, so power has to be added. So we have 10 to minus 6. So our final answer is simply 120 microfarads. So this is how you can approach this problem. For the second part, we need to calculate resistance in kilo ohms. But for this question, we have already calculated the time constant that was equal to 5.5 seconds, and we have calculated value of capacitance that was equal to 1.2 times 10 to minus 4 farads. Now we need to calculate resistance. So simply in this case, we need to understand tau. This is equal to R times C. We need to calculate resistance now. So resistance simply will be equal to tau divided by capacitance. Tau is equal to 5.5 seconds and capacitance is 1.2 times 10 to minus 4. So our final answer in this case will be equal to 45,800 ohms. That answer has to be in kilo ohms. So we can write down this one 46 kilo ohms up to 2 SF. So the final answer for this one is 46 kilo ohms. For question number 7, part A, we need to define magnetic flux density. And this question is very common in past papers, so you need to understand how to define magnetic flux density in a proper way. So let's try to define this one in a very nice way. So simply we can start with magnetic force. Magnetic force is equal to VIL sine of theta. We need to define magnetic flux density, so we can make B the subject. So we can say B is equal to F over I times L times sine of theta. If I is the unit current, magnetic flux density is a quantity, so you have to define this one in terms of quantities. And if length of the wire is also unit length, and if the angle between conductor and the field is 90 degrees, means theta is equal to 90 degrees. If conductor is placed at 90 degrees to the field, or simply you can say if the angle between current and the field is 90 degrees, then the force experienced by a wire of unit length with unit current passing through the wire, that force will be equal to magnetic flux density in magnitude. So this is what you need to understand. So simply you can write down in this form and then you can write down your proper answer. So let me show you the answer, how you need to write down your final answer. This is how you need to write down your final answer. So what we have written here, we have said is the force experienced per unit length by a long straight conductor carrying unit current placed at right angles to the field at that point. So this is how you can define. So if you write down this one, you will get 3 marks. So important is the force experienced by the wire per unit length unit current passing through the wire, and the wire has to be placed at 90 degrees to the field. So this is how you need to define. For part B, it is given to us an insulated rectangular coil of wire consisting of 40 turns is suspended in a cradle from a Newton meter as shown in figure 7.1. The vertical side of the coil have a length of 5.0 centimeters and horizontal sides have a length of 3.00 centimeters. The initial reading on the Newton meter is also given, that is equal to 0.563 newtons. For this question, it is also given to us a U-shaped magnet rests on a top band balance that is set to a reading of 0.00 gram. What exactly it means? It simply means that we have a top band balance. So this one is the top band balance. So this is the scale, and we place a magnet on this top band balance. So this one is the magnet, U-shaped magnet, and we set reading on this one equal to 0.00 grams after placing the magnet. So it is set to a reading of 0.00 grams. It is also given to us the lower edge of the coil is lowered into the region between the poles of the U-shaped magnet as shown in the side view in figure 7.2. The magnetic field in the region between the poles is uniform. The lower edge of the coil is inside the uniform magnetic field. Current of 3.94 is now passing through the coil. This causes the reading on the top band balance to change to 2.16 grams. So in this case, reading on this top band balance increase. It simply means that the force on the magnet is down, so the force on the wire will be up. So force on the wire is up, and the coil inside the magnetic field is placed like this. So we are looking at the side view. In this case, it is given to us force is up. If the force is up, so it means that magnetic field can be from left to right, or magnetic field can be from right to left. That is not given to us. So if magnetic field is from left to right, so current will be out of the page. And if magnetic field is from right to left, so current has to be into the page. So that is not given to us. But one thing we need to understand is that magnetic field and current, they are in one plane, and the force is in another plane. And force is perpendicular to the magnetic field, and force is also perpendicular to current. So simply you can understand with the help of left-hand rule, Fleming left-hand rule. So if current is into the page, so magnetic field direction has to be from right to left. If current is out of the page, direction of magnetic field has to be from left to right. Then force will be up. Because we only have direction of force, so we have two possibilities for direction of magnetic field and also for direction of current. But one thing is 100% right, that the force is perpendicular to the magnetic field. Force is also perpendicular to current. So this point we need to understand, and this is based on Fleming left-hand rule. Now question is asking us, explain why current causes a vertical force to act on the coil. Because force has to be perpendicular to the magnetic field, force has to be perpendicular to current. So this is according to Fleming's left-hand rule. Now we can simply write down our answer in this case. Current in the coil is perpendicular to the magnetic field. So in this case we have current. So if current is, for example, into the page, so we can say if current is into the page. So simply you can see in this case, if current is into the page, so the magnetic field, this will be from right to left. So there will be force, that one will be upwards. So force in this case is up, so we can write down this is one possibility. Second possibility is, so this current is into the page, so this is into the page. Second, if current is out of the page, then magnetic field can be from left to right. So as you can see here, so magnetic field from left to right. In this case, force is also up. So we can simply say, as current is perpendicular to the field, it means there is force on the wire, and force on the wire is perpendicular to magnetic field and current. Simply Fleming left-hand rule. So let me show you the answer, how you can write down your answer. This is how you can write down your answer. You can say current in coil is perpendicular to magnetic field, so there is a force on the wire. Force on the wire is perpendicular to current and field, so force is vertical. So magnetic field and current, they are in one plane, and force is perpendicular to that plane. So this this is what you need to understand, and this is how you need to answer. For the second part, we need to determine up to 3 significant figures the flux density of the uniform magnetic field. But for this question, it is given to us that the increase in reading of top band balance, that is equal to 2.16 grams, and this increase in reading of the top band balance is due to vertical force only, and the vertical force will be experienced by only this part of the loop. So there will be vertical force on this part of the loop upwards, but the force on this side of the coil will be in one direction, and force on this side of the coil will be in the opposite direction. So only we need to consider force acting on this part of the wire. So simply we can equate forces. So in this case, the magnetic force, this one will be equal to mg. Magnetic force is equal to NBIL, and this is equal to mg. We need to calculate value of B, so simply we can make B the subject. We can write down B will be equal to mg divided by NIL. In this case, M is given to us, means the reading of top band balance is given, that is equal to 2.16. This is in grams, so we have to multiply with 10 to minus 3, and value of G we have to use 9.81. This coil has 40 turns, so we can write on 40, and current in the coil is given, that is equal to 3.94, and length of this side of the wire, because this side is only experience, this side will only experience vertical force, so we have to take this length of the wire, and that is equal to 0.03 meters, because this is 3 centimeters, so we divide it by 100, so this is the answer. Now if we simplify, we just use calculator, our final answer will be equal to 4.48 times 10 to minus 3 Teslas. So this is our final answer. So the tricky part only is we need to understand increase in reading of top band balance, and that is due to only vertical force, and vertical force is experienced by this part of the wire, so you have to take length of this part of the wire only. So then just plug in numbers and you can find the answer. So the answer for this question is 4.48 times 10 to minus 3 Teslas up to 3 SF, because this data is up to 3 SF, you can see it as 3 SF, so that's the reason our final answer also has to be up to 3 SF. For the last part of this question, we need to determine what is now the reading on the Newton meter, and we need to explain our reasoning. When there was no magnetic force acting on the coil, the force acting on this coil is only the weight of the coil, so we can simply draw. When there is no magnetic force, only force acting on the wire, that is equal to weight of the coil, and weight of the coil is acting vertically downwards, and the magnitude of weight is given, that is equal to 0.563 newtons. So this is the reading on Newton meter when there is no magnetic force acting on the wire. But we have already discussed there is a force acting on the magnet, that is downward, so there is a reaction force acting on the coil, that has to be vertically upwards, and these two forces, they have to be equal in magnitudes. So we can say the force acting vertically upwards on the wire is equal to 2.16, because this is the mass, we have to multiply this one with value of G. So this is the mass, we have to multiply this one with 9.81. So the reading on Newton meter now is the resultant of these two forces. So simply we can say the reading on Newton meter is equal to the resultant force acting on the coil. In this case, this force is bigger, so we can write down this is 0.563 minus, we have 2.16 times 10 to minus 3 times 9.81. So we can calculate the reading on Newton meter. In this case, reading on Newton meter will be equal to 0.542 Newton. Our answer has to be up to 3 SF, because we have least number of SF in raw data is equal to 3 SF. So this has 3 SF, this also has 3 SF. So our answer has to be up to 3 SF. So this is how you can write down the final answer. So very nice question, conceptual question. If your concepts are not clear about electromagnetism, this question is quite tricky and challenging. And this question is very nice question to improve your conceptual understanding of electromagnetism. If you watch this video once, you couldn't understand or you couldn't get all the points, you can do this question again by yourself and watch the video again. You will understand the concepts about electromagnetism in the proper way. I hope you will find this video helpful, and if this video is helpful, please like and subscribe because your encouragement is very important. More encouragement, more videos will be coming for you in the future. See you in next video. And I will try to finish this paper as soon as possible, so I will be uploading remaining questions as soon as possible. See you in next video. Bye for now.